At 6:18 p.m. on January 1st, 2026, seismometers across eastern Sicily registered something extraordinary. Not an earthquake, not a volcanic explosion, but a fissure opening at 2,100 meters elevation on Mount Etna's eastern flank, unleashing a river of molten rock into the Valle del Bove at speeds that made veteran volcanologists hold their breath. What those scientists knew, but weren't saying publicly, was that this wasn't just another eruption. It was a symptom of something far more terrifying unfolding beneath the Mediterranean Sea. Because while the world watched lava flows descending towards sleeping villages, underwater sensors 12 kilometers offshore were recording movement that defies everything we thought possible. Mount Etna, all 140 billion tons of it, is sliding into the sea. And the latest data suggests we may have far less time than anyone imagined. Here's what makes this a true nightmare scenario. The same German research team that first detected Etna's submarine slide in 2017 has now confirmed that the movement is accelerating. In just 8 days back in May 2017, the southeastern flank slipped 4 centimeters. That's the equivalent energy of a magnitude 5 earthquake, happening completely without a tremor, without a single seismic warning. The mountain has learned to collapse in silence. But the January 2026 eruption changed everything. As lava poured from that low-altitude fissure, submarine monitoring stations recorded simultaneous displacement deep underwater. The connection is undeniable. Every time Etna erupts, its flank slides faster. The volcano isn't just active, it's tearing itself apart from the bottom up, one eruption at a time. And gravity, not magma, is pulling the trigger. The question facing 1 million Sicilians living on Etna's unstable slopes is no longer academic. How much time do they actually have? And why are scientists now warning that this collapse could unleash the deadliest tsunami in Mediterranean history, engulfing coastlines from Greece to Libya in a matter of minutes? The breakthrough that exposed this existential threat began in 2016, when Dr. Morelia Urlaub's team from Geomar Helmholtz Center for Ocean Research installed 5 underwater transponders across the seafloor off Etna's southeastern coast. For 15 months, these precision acoustic devices pinged the ocean floor every 90 minutes, creating humanity's first real-time map of a volcano's submarine movement. What they captured in May 2017 was something no human had witnessed before. A volcanic flank sliding seaward as it happened, 4 centimeters over 8 days, without a single earthquake to warn of its motion. The data revealed a terrifying pattern. Etna's southeastern slope is moving as a unified block toward the Ionian Sea, and the displacement increases the farther you get from the volcanic summit. That's the exact opposite of how volcanic instability should behave. If magma pressure were driving this collapse, movement would be greatest near the magma chambers at the peak. Instead, the fastest sliding is happening 12 kilometers offshore, at depths of over 1,200 meters, where the volcano's underwater foundations are literally dissolving beneath the weight of the mountain itself. Even more disturbing, the submarine fault extends over 30 kilometers into the Mediterranean, far larger than any previous geological surveys had predicted. As geophysicist Hydron Kopp puts it, the entire slope is in motion due to gravity. It is therefore quite possible that it could collapse catastrophic, which could trigger a tsunami in the entire Mediterranean. And here's what keeps scientists awake at night. This slippage is happening entirely without earthquakes. The acoustic displacement data shows a silent event with energy equivalent to a magnitude 4.3 to 5.3 earthquake. That's enough force to level buildings on shore. Yet it's all occurring underwater without so much as a detectable tremor. The mountain is collapsing in a seismic whisper. To understand why Etna poses such an unprecedented threat, we need to rewind 8,000 years to when the volcano's eastern flank last failed catastrophically. That collapse carved the Valle del Bove, a 4-kilometer wide horseshoe scar on Etna's eastern slope that's visible from space. Landslide deposits from that single event extend 25 kilometers underwater, with a total volume equivalent to 500 Empire State Buildings plunging into the Mediterranean simultaneously. The tsunami generated by that ancient collapse left traces on coastlines across the eastern Mediterranean. Marine archaeologists have identified destruction layers in ancient settlements along the coasts of Greece, Turkey, and even as far as Israel, over 1,000 miles away. Entire coastal communities were erased in a matter of hours. Since then, Etna has settled into a rhythm of frequent summit eruptions, alternating with rarer but more destructive flank eruptions. Historical records show at least 60 lateral blasts since 1600 alone. The infamous 1669 eruption sent lava streaming into Catania and permanently altered the Sicilian coastline. More recently, significant flank events in 1928, 1971, 1981, and 1991 involved magma rising through cracks on the volcano's sides, clear signs of mounting structural instability. But what's happening now is uncharted territory. Never before have scientists observed a volcano's flank sliding seaward so relentlessly without any link to magmatic activity. This is pure gravitational collapse. The mountain's own weight is tearing it apart along deep-sea fault lines that scientists didn't even know existed until 2017. Over the last 24 months, the movement has dramatically accelerated. Coastal GPS stations now record a relentless millimeter-by-millimeter creep toward the sea. Satellite radar imagery shows the entire southeastern slope deforming coherently seaward. In 2025 alone, Etna erupted 3 major times, each event correlating with measurable increases in flank displacement. The June blast launched an ash plume 21,000 feet high, while submarine sensors registered a simultaneous speed up below the waterline. Then, on June 2nd, a pyroclastic flow generated by a collapse at the northern flank of the southeast crater traveled 2 kilometers in just 1 minute, interacting explosively with buried snow. Then came January 1st, 2026. As revelers celebrated the new year across Sicily, Etna opened a fissure near Mount Simone at 2,100 meters elevation. The lava flow that poured into Valle del Bove descended to 1,420 meters within 24 hours, the lowest altitude eruption in decades. What terrified volcanologists wasn't the lava itself, but what their submarine sensors detected simultaneously. The underwater portion of Etna's flank was moving again, pulled downslope by the redistribution of mass from the surface eruption. Dr. Boris Benke, a leading volcanologist monitoring the eruption, noted that the lava appeared incredibly close to foothill villages like Milo and Fornazzo. In reality, the most advanced lava front remained 5 kilometers away, but the visual illusion highlighted a deeper truth. Etna's collapse zone extends from 3,300 meters at the summit, all the way down to depths of 1,200 meters below sea level. Nearly 4,500 meters of vertical, unstable terrain, all sliding toward the Ionian Sea as a single coherent block. Leading experts are now sounding unprecedented alarms. Dr. John Murray of the Open University, who has studied Etna for over 3 decades, calls the prospect of catastrophic flank failure absolutely devastating. Dr. Urlaub herself has issued a chilling public warning. She says we cannot exclude flank movement evolving into catastrophic collapse. The Italian National Institute of Geophysics and Volcanology minces no words, declaring Etna's seaward slippage poses a much greater hazard than previously thought. But it's not just the velocity of Etna's collapse that has scientists terrified. It's how far the mountain has already moved. According to Dr. Urlaub's calculations, the southeastern flank has slid a staggering 4 meters since her team's monitoring began in 2016. An astounding distance for a landmass weighing tens of billions of tons. Even more concerning is evidence that Etna's ancient flank failures may have been preceded by similar slow, steady slippage. Core samples drilled from the volcano's submarine flanks reveal layers of rubble and debris up to 300 meters thick. Mixed within this volcanic detritus are ancient soils, river deposits, and even fossilized tree trunks, the remnants of entire landscapes carried to the bottom of the Mediterranean. The implications are chilling. As Dr. Murray explains, these deep-sea deposits suggest Etna's prehistoric collapses involved not just the submarine flank but massive portions of the onshore volcano as well. We could be looking at a scale of failure we have never seen in modern times, he warns. With so much land already in motion and millennia of geological evidence pointing to past mega-collapses, the question facing eastern Sicily is no longer if Etna's flank will fail, but when. Dr. Erlaub sums it up bluntly. It is not a matter of if, but when. And right now, all signs point to sooner rather than later. The stakes are nearly incomprehensible. If the entire 250 square kilometer sliding flank were to break off at once, it would be the single largest landslide in recorded history. The resulting tsunami would be equally unprecedented. Using advanced computer modeling, French geophysicist Dr. Raphael Paris has created virtual simulations of Etna's flank failing all at once. The results are apocalyptic. The initial wave generated by this collapse reaches an astonishing 250 meters tall as it barrels toward the Ionian shoreline at speeds exceeding 400 kilometers per hour. Within 10 minutes, a wall of water 50 meters high would crash into Catania, flattening Sicily's second-largest city instantly. Even 30 minutes after the collapse, 20-meter waves would be battering the coasts of Greece and Libya. Dr. Paris grows somber as he considers the human toll of such a catastrophe. In our simulation, we estimate casualties could easily top 1 million in the first 2 hours alone. By the end of the first day, the numbers are difficult to even conceptualize. It would be a humanitarian disaster unlike any in modern European history. Yet, what makes Etna's threat so insidious is that even a much smaller flank failure could still unleash untold devastation. A collapse involving just 10 to 20% of the sliding rock mass, a volume consistent with many prehistoric events, would still yield 40-meter tsunamis slamming into eastern Sicily. Even this more moderate scenario would rank among the top 5 natural disasters in European history, jeopardizing up to 250,000 lives and causing hundreds of billions in economic damage. The sheer range of possible outcomes is one of the most daunting challenges facing volcanologists and emergency planners. How do you prepare for a catastrophe that could unfold over hours, days, or decades? How do you evacuate 1 million people from an impact zone larger than some European nations? The grim calculus of Etna's flank collapse requires confronting possibilities that once seemed unthinkable. Today, 1 million people live in the shadow of Etna's unsteady slopes, many of them in towns and villages sitting directly above the sliding flank fault. Densely populated communities like Zafferana Etnea, Via Grande, and Giare all lie within the highest risk collapse zone. Sicily's second-largest city, Catania, sits just 30 kilometers south of the most geologically unstable terrain. The Catania metropolitan area is home to over 300,000 people with hundreds of schools, hospitals, and critical infrastructure facilities all within reach of the tsunami zone. The single evacuation route for much of this population is Highway 120, a narrow road that winds directly through Etna's active eastern flank. Even a minor eruption can render this lifeline impassable. If the mountain's seaward slippage suddenly accelerates, escaping the danger zone may become impossible. When Etna finally collapses, the scale of destruction would be almost unimaginable. In an instant, billions of tons of rock would plunge into the Ionian Sea, displacing a monstrous volume of water. The resulting tsunami would reach 30 meters in height before slamming into Sicily's eastern shores just 5 minutes later. From there, the waves would race outward in an ever-expanding radius of death. Malta and southern Italy would be hit within 15 minutes. Within an hour, every coastline in the eastern Mediterranean would be engulfed, from Greece to Libya to Egypt. Current models predict over 20 million people across 6 nations would face severe flooding, with thousands of kilometers of densely developed shoreline at risk. Economic losses would soar into the trillions as ports, refineries, and transportation networks are smashed by the waves. And all this destruction would unfold with almost no warning. The Mediterranean currently has no integrated tsunami alert system, and the submarine sensors that might detect a flank collapse are not connected to any hazard mitigation network. The result would be a cascading infrastructure failure of epic proportions. Sicily's electrical grid, heavily dependent on now destroyed coastal power plants, would crash within minutes. Water treatment facilities would be contaminated just as broken pipelines lose pressure. Roads would become death traps as drivers flee the coast, while hospitals and emergency services are paralyzed by power outages and fuel shortages. Across the Mediterranean, ports would shut down, severing the maritime trade routes that are the region's economic lifeblood. Overnight, Southern Europe and North Africa would face a refugee crisis not seen since World War II as millions of survivors seek safety inland. This is the nightmare now lurking beneath the Mediterranean, one that could be unleashed in the geological blink of an eye. It is a threat that scientists are only beginning to understand. The difficulties of predicting such a catastrophe are immense. Unlike earthquakes or traditional eruptions, flank collapses do not telegraph their final failure with increasing tremors or accelerating fault movement. In Etna's case, the transition from gradual creep to sudden collapse could occur with scarcely a seismic whisper. This tragic lack of warning signs has left researchers scouring Etna's geological history for clues. Dr. Julia Crummy of the British Geological Survey has meticulously dated past flank collapse deposits using paleomagnetic signatures and volcanic ash chronologies. Her findings paint a sobering picture. While smaller submarine landslides occur relatively frequently around Etna, at least once every 1,000 years, the mountain's catastrophic mega-collapses follow a significantly longer rhythm. The last comparable event, which created the Valle del Bove, happened 7,600 years ago. The one before that has been dated to 15,000 years ago. As Dr. Crummy sees it, we are confronting the possibility that Etna is now primed for another Valle del Bove scale collapse. In geological terms, the mountain is overdue for a full flank failure. Even more concerning, the time between Etna's last two mega-collapses was 2,000 years shorter than the interval separating its last catastrophic failure and today. Dr. Crummy's research also underscores a haunting parallel. The period preceding Etna's collapse 7,600 years ago was marked by a sequence of increasingly violent eruptions, a pattern that bears striking resemblance to the volcano's activity over the last 150 years. For Dr. Crummy, the implications are clear. We have to consider the possibility that Etna's recent eruptions are not just isolated events, but warning signs of a major structural failure already in progress. Right now, as you listen, a battery of GPS stations, seismometers, and satellite sensors are all aimed at Etna, searching for the slightest twitch that might signal an impending disaster. German and Italian research teams are rushing to deploy even more submarine monitoring equipment, not just at Sicily, but near other slumbering giants like Stromboli and Vesuvius. Yet even with these herculean efforts, science still cannot predict when slow slippage might accelerate into sudden collapse. Dr. Erlob is blunt. We just have to keep an eye on Etna's flank and how it is moving. Her team is now scouring the data for hidden patterns that could serve as early warning signs. They are tracking how eruptions and earthquakes affect flank movement, watching for any spike in slippage rates. Satellites scan the mountain for new fractures and thermal anomalies that could indicate structural failure. Volcanic gas emissions are monitored for the slightest uptick that might correlate with unseen fault activity. Early warning is the goal. The chilling implication is that Etna may represent an entirely new class of risk. Flank collapse with minimal magmatic warning. If so, then coastal volcanoes worldwide may be silently sagging seaward right now, undetected. The same factors destabilizing Etna, gravity, structural weakening, and prehistoric slip faults threaten iconic peaks from Kilauea to Mount Fuji to Vesuvius. It's a staggering thought. Entire mountains, millions or even billions of years in the making, could slide into the sea while we watch from above, unaware. They may collapse not with the roar of eruption but in awful silence as their foundations simply dissolve. Yet that is precisely the scenario that Etna's data now forces us to confront. It demands action from scientists, civil authorities, and ordinary citizens alike. One thing is clear. We are all, in a sense, living on the slopes of Etna now. Dr. Murray reminds us that catastrophic volcanic collapses occur worldwide about 4 times per century. Dr. Erlob warns that the hazard might be underestimated at other coastal volcanoes. The challenge, and the urgent necessity, is to close the gaps in our understanding before the next collapse strikes. If Etna's slow-motion disaster has taught us anything, it is that the solid ground beneath our feet may be far more fragile than we ever dared imagine. But there is still reason for hope. Around the world, scientists are mobilizing on an unprecedented scale to meet this emerging threat. Coastal communities are beginning to integrate flank collapse scenarios into their tsunami preparedness plans, and public awareness of these hazards is growing every day. Here in Sicily, a new sense of urgency now infuses the work of civil authorities and emergency responders. Detailed evacuation procedures for eastern Sicily are being updated and drilled in cities and villages alike. Underwater seismic networks are being expanded with the ultimate goal of enabling real-time tsunami alerts for the entire Mediterranean basin. Yet even as we race to prepare for the unthinkable, we must also confront an unsettling truth. No amount of planning or mitigation can eliminate the risk that Etna and other coastal volcanoes now pose. We are living, quite literally, in the shadow of mountains that could come crashing down at any moment. Perhaps that is Etna's most profound lesson and its most urgent warning. In an age of rapidly accelerating climate impacts and ever more complex infrastructure interdependencies, we are all now inherently vulnerable to catastrophes that once seemed unthinkable. Whether it is rising seas, superstorms, or collapsing mountains, the message is clear. The time to prepare for previously unimaginable disasters is now. Because on a planet in flux, complacency is a luxury we can no longer afford. As the January 2026 eruption demonstrated, Etna is not waiting for us to be ready. The mountain is speaking. The question is whether we're listening closely enough to hear what it's trying to tell us before it's too late.